For example, if we were to look at the helium atomic absorption spectra, okay, the helium Aa spectra, we know when helium goes through its principal transition, from the ground up, right? It goes from 1s2 to 1s1 plus 2s1. Okay? So what is this 1s1, 2s1 state? Well, because that's occupying both a 1s orbital and a 2s orbital, it could be spin parallel, like a triplet. That would be a triplet state. Or, and because these are in different orbitals, they could in fact still be paired. Not necessarily, or spin correlated, right? Not necessarily in the same orbital, but all the same, that is a possibility, okay? And what's pretty cool, when we observe this helium Aa spectra, you have to have a really high resolution to do it, but you get a doublet. So, to us, if we're to zoom way out on that peak, like, so I'll this picture means like I'm zooming way out, then I might just have a really sharp looking peak, right? Like one single transition corresponding to this 1s2 going to 1s1, 2s1. But if I were to zoom way in on that, I would actually see that there is a doublet. And that doublet is due to the fact that we could have this 1s1, 2s1. It could be a triplet, or it could be a singlet. So we could get transitions to either of those cases, okay? And we have to now come up with an organized way how we can notate which one it is. Is the 1s1, 2s1 excited state a triplet state, or is it a singlet state? How do we know, and how do we notate that? That's where we're going to go next, okay? And just to give you a preview, that's where we're going to have to get into this total spin quantum number J. Okay, so that is coming next, folks. I will see you in the next video. Okay, so what is spin-orbit coupling? Well, recall that I've kind of been describing this electron system as kind of like very similar to the Earth-Moon-Sun system, okay? Or really, I should just say the Earth-Moon system, right? So we know that the electron is rotating around the nucleus, and so that gives it angular momentum given by L. But also the electron has its own intrinsic spin, okay? So it is also spinning given by quantum number S. And so we come up with this new quantum number to describe the total angular momentum, which is J and mj, okay? So, and for this very simple system here that I've highlighted, which is all that we're going to get into in this class, we have a high J and a low J. And the high J is given by when both the angular momentum and the spin are parallel, right? So both angular momentums are pointing in the same direction, and there is a resulting magnetic field given by these green arrows that ensues. And that magnetic field is, they're both aligned, and the angular momentums are both aligned, okay? And as we shall see, this ends up corresponding to a higher energy state. Then we have the low J, and the low J is given when the electron is spinning in the opposite direction as it's rotating, okay? And so now you end up creating these competing magnetic fields as well as competing angular momentum, all right? And so J is given by L plus S minus 1 all the way down to L minus S. And mj takes on all values j down to j minus 1 all the way to negative j. And just like we did with L and S, there's total magnitude from the total spin j, And there's also the component on the z-axis given by mj h bar. All right. So let's see here. Did I cover all of my bases? Okay, great. So moving on, let's look at a realistic example. Oh, and then I think that I forgot to give you an equation here. I don't see it written down, and that's okay. I'm not going to worry about the equation. So here's a realistic example. The sodium D lines, and this is the very famous, lovely yellow sodium glow that we're used to seeing in a flame, right? And it's approximately 590 nanometers. Okay. Well, as it turns out, when you look at sodium, sodium ground state, all right, and we'll say, sodium solid, 1s2, 2s2, 2p6, 3s1. This creates a doublet. And the reason why this is a doublet state is because we know that we've got this 3s1, there's one unpaired electron, and that electron can be spin up or spin down, and we don't know which is which. Both are acceptable, okay? So that makes the doublet state. Any one electron system makes a doublet state, and hopefully what you remember, any two electron system can either make a singlet, in the case of it being paired up, or a triplet, in the case of them being non-paired up, like parallel spins, okay? So when we excite sodium, it can go through many transitions, right? But the most notable one is going from this 3s1 to 3p1. And when the electron falls back down from the 3p1 state back to the 3s1 state, so I'll note that by saying 3p1 energy level, 3s1, that creates the sodium D line, that lovely yellow sodium color that we're so used to seeing. Well, as it turns out, because it's a doublet state and its electron spin can be correlated with the angular momentum, as in the high J value, or it can be uncorrelated with the spin angular momentum, the low J value, we actually get two possibilities, okay? And so if you recall, J equals L plus S all the way down to L minus S. And so now if we can see, we're talking about a p orbital, right? So that means that L equals, let's see, 1. And S is always 1/2. So 1 plus 1/2 gives us 3/2 for the high J value, right? And then, of course, it goes all the way down to L minus S. So that means our J can be 1 minus 1/2. So all the way down to 1/2, okay? And the spin orbit coupling is given by this equation, plus 1/2 hc angstrom minus hc angstrom, or A, excuse me, A is the spin orbit coupling constant. So spin orbit coupling constant. And there's a formula for that constant, but I'm not going to worry about it so much, okay? And so what we see, because of these two possible spin states given by the doublet, the 3p1 level is split. And it's split into that high J value, which is actually higher in energy, and it's split into the low J value, which is lower in energy, all right? And so you can see that given here by this term symbol, which is where we're going next. And what's important to note for now, because you don't know about term symbols, here that 3/2, that corresponds to the J 3/2, and here that 1/2, that corresponds to the J 1/2. And so what you would actually observe in that sodium yellow line, if you had a very fine monochromometer or a very highly resolved detector, you would actually see that line as a doublet. There is actually two of those yellow lines occurring at 589.76 in the case of the low J state going back down to the ground state, and 589.16 in the case of the high J state going back down. And remember, because that's a smaller wavelength, it's a higher energy. So there's no way we observe this with our eyeballs, right? We're not going to be able to resolve, what is that, 0.6 nanometer difference with our eyes. There's no way we can do it. And even a lot of the monochromometers that we use, particularly in the general chemistry lab, they can't even resolve this. You have to have a really high resolution detector and monochromometer to tell the difference between these two spins, all right? And what I also want to point out, this term symbol, okay, we're going to use these things as an organized way to note all of these characteristics of the atom, such as what is its J value, what is its spin state, etc. Okay, and so that's where we're going next.